What's up, everyone? Welcome back to Math 18A College Algebra, another online lecture. It's now the end of our first week of shelter in place. I hope you guys are all still doing okay. I'm still doing okay over here. I have managed to become even worse about procrastinating, so that's not so good. But without further ado, let's continue on Chapter 3. We're going to do 3.2 today. Okay, so 3.2 covers polynomial functions of higher degree, so higher than like quadratics like we saw last section. And remember that polynomials are just functions that look like an x to the n plus blah 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 plus, it's all powers of x with coefficients, real coefficients. And so one of the first concepts that I want to introduce is continuity. And so polynomials are all what we call continuous. And continuity just means that your graph doesn't have any breaks in it. And I'll show you an example of what that looks like looking at a graph. So let's take one of our normal graphs that we see quite often. This would be f of x equals x squared. So notice how this graph is smooth. It has no breaks in it. So that's what we call continuous. So this one is continuous. And let's look at an example of a graph that is not continuous. So one of the main examples that you'll see for these are called piecewise functions. Piecewise functions. And so those are functions that are defined differently depending on what value of x you're sitting at. So let's say we have this piecewise function f of x equals, let's say that it's x squared on the interval 0 less than equal to x up until 2. So we know what x squared looks like, but we're only going to define it for this interval that we have here, 0 to 2. So we know x squared starts at 0. And then at 1, it's 1. At 2, it is 4. And here we'll put an open circle, because we're not actually including this 2 in our interval. And let's put the second part of the function, let's call that, let's just say f of x equals 1 for 2 less than x less than, just go all the way to infinity. So then starting at 2, my function is just 1, this horizontal line. And we'll say it just goes to infinity like this. So clearly you can see that this function has a break right here at this x equals 2 value. So that means that this function is not continuous. And you'll see this in calculus quite often. So if you're moving on to business calc, this is a good concept to know. And so here, even though we've defined our f of x to consist of polynomials, like this x squared is a polynomial, this 1 is technically also a polynomial, we wouldn't say that f of x is a polynomial because of this break here. We've shown that it's not continuous, and polynomials have to be continuous. So f of x here is not a polynomial. But for the rest of this section, we're going to be focusing on polynomials. So now let me remind you of something that I covered back in chapter 2, I believe. It's how we can classify a graph just based on the degree of the polynomial and the sign of the leading coefficient. And I made a chart in class when we talked about this, so let me recreate that just roughly here. So you can have degree and sign. Split it into sections like this. So your degree can either be even or odd. And your sign can either be positive or negative. And we can tell pretty much all that we care about a graph just based on these things. So remember, if you have an even degree, your tails point in the same direction. And if you have a positive sign, then it's going to be something like this. I had it in class like this bowl shape. But you can have more wiggles in it too, as long as your tails both point upward here. And so for negative, it's just the opposite direction. Your tails still point in the same direction, but they're pointing downward here. And so, yeah, all even degree polynomials look something like this. So the quadratics that we've seen only have that one like hump in it, basically. So yeah, these are just higher degree ones. And so if you have odd degree, your tails point in opposite directions. And so positive sign means you start pointing downward on the left and you go up on the right. So tails point in opposite directions. If you have a positive leading coefficient, you start at the bottom and you go to the top. And it'll be the exact opposite with a negative leading coefficient. So start at the top, do whatever you want in the middle, go downward at the end. So your tails point in opposite directions here. And to be consistent with your textbook, this is called the leading coefficient test. So if they ask you to apply the leading coefficient test, this is what they're asking you for. Leading coefficient. And so after this, the leading coefficient test, there's only one more thing that you really need to know to be able to tell exactly what a graph of a polynomial looks like. And that's just, where are my x-intercepts? So if I know where it touches this x-axis here, then I know everything there is to know about my polynomial graph. So the x-intercepts, we tend to refer to them as the real zeros of a polynomial function. So this is where factoring comes in again. If you know how to factor a polynomial, you can find its zeros. Function. So just to be clear, when I talk about like f of x, a polynomial function, with your coefficients, like a sub n, have to be real. A sub n in the real numbers, that fancy R means real numbers. To say each of these things means the exact same thing. So x equals a is a 0. Of your function f of x. X equals a, whoopsie, is a solution to f of x equals 0. X minus a is a factor of f of x. And the point a comma 0 is an x-intercept. of your function f of x. So all of these, they all mean the same thing. So whenever we're looking for x-intercepts, we're looking for where your f of x is equal to 0, right? So same thing here, you're looking for your zeros. You're looking for a factor, x minus a, so that your f of x equals 0. So let's now take a look at an example from a past final exam. And I claim that if you find a problem like this on your final exam, this will be one of the easiest problems that you'll find. So it says, consider the polynomial function f of x equals x plus 1 times x minus 3 times x plus 4 times x minus 5 times x minus 11. And it asks us to list the real zeros of f. So the first thing to notice is that your f of x here is already factored for you, right? They just listed out each factors and they're all multiplied together to be your polynomial function. And let's go back to our list of statements here. We have all these factors. X minus a is a factor of f of x. Well, that's the same thing as saying that x equals a is a 0 of f of x. And we want to list the real zeros of f. So you should just be able to pick off each 0 of f from here. So your zeros would be x equals, what number is going to set this equal to 0? Negative 1. What about this one? X equals 3. This one, x plus 4. Well, I need a negative 4. X minus 5. That's going to give me a 5. X minus 11. That's going to give me 11. So it's just setting, it's like we've done before. You just take each one separately, set it equal to 0. And that'll give you all the real zeros of f. Okay, so then part B asks us to sketch the graph of this polynomial and clearly label the zeros. So let's go to a new page. Take up the whole page with my graph here. Okay, so let's first apply our leading coefficient test. So that's a little bit less straightforward to see here, but you just have to look at how many x's you have, and that'll tell you the degree. So I have 1, 2, 3, 4, 5. 5 x's, right? So I have x to the 5th with some coefficient. Maybe I don't know what that is yet. But the leading coefficient on all of these x terms is just 1, right? There's no extra number here. There's no like 2 or anything. If it was 2, it would be different, but it's not. They're all just 1. So then if I multiplied all of these out, the leading coefficient of my x to the 5th term would be 1. And that's the highest degree term that I'm going to get from this. If I multiply, like FOIL out everything, I'm not going to get anything higher than x to the 5th. So this is essentially the only one that I care about. Plus whatever, right? Okay, so, okay, yeah, first let's do our leading coefficient test then. Leading coefficient test. So I have odd power, right? And positive leading coefficient. So odd power, or odd degree. Positive sign. So I already know my tails point in opposite directions. Let me go over here, I guess. Tails point in opposite directions. And since it's positive, it starts at the bottom, does whatever in the middle, and goes up from there. Right? So now, I just want to know where these x-intercepts occur, which is exactly what we solved for in part A. So each of these is an x-intercept. So I just need to plot those on my x-axis. So -1 was one of them. 3, -4. So 1 at 3, 1 at -4. And then 5 and 11. So 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So then coming from the left, student green, I know that my tail has to come from the bottom. It's going downward on the left. So it's going to go from down through this 4. It has to turn around and hit this -1. Turns around again. Hits this 3. Oh, I had one at 5, so I need to turn around and hit 5. Forgot to plot that one. And then turns around one more time, passes through 11, and goes off to positive infinity. And let me just plot this one at 5, so we're all clear. So this is what my polynomial looks like, essentially. I don't know how tall it gets, but it doesn't really matter in this case. We're not too worried about that. So this is a perfect sketch of what your polynomial looks like. Okay, and so one of the last important concepts of this lecture, before I finish up with some examples, is multiplicity and repeated zeros. So a repeated zero is what happens when you have something like x minus a to the k, some power that isn't just 1, equal to 0. So I know that x equal to a is 0 of this polynomial, but it doesn't just happen once, it happens k times. So in this case, x equals a is what you call a repeated root, or a repeated zero. And you say that it has multiplicity of k. So some new terminology here, repeated zeros and multiplicity. So just a quick example, if I had x minus 2 to the, let's just do squared first. Well then, x equals 2 is a repeated zero, right? And it has multiplicity 2. And so this multiplicity changes slightly what your graph looks like at that point. This would be, instead of just crossing through the value, the x-intercept, x equals 2, it does what we call bounces. So it goes like this, right? It doesn't cross through, whoops, like that. It doesn't do that. It does a bounce. So it touches the 0 and then it comes back up. And so notice that this actually makes a lot of sense using the logic that we learned from, what was it, transformation of functions, transformations. So this is actually a horizontal translation. Let me put that like down here. Translation of the graph f of x equals x squared, right? This is a shift. It shifts it 2 to the right. Sorry, I'm going really low on the page here. But that sort of explains like why our even degrees do this bouncing thing. It's all about the multiplicity of the zeros. And if you had like, if this was actually x minus 2 to the 4th, it's the same thing. It just does this bounce. The even ones do a bounce, and the odd ones pass straight through. So let me write that on a new page. If it's even, you have what's called a bounce, like you. So that's where you touch the 0, but you don't cross it. Like touch 0, don't cross. Whoa, cross. And if you have odd, if it is odd multiplicity, then you cross it. You like pass through. So like touch 0. And cross to the other side of the axis. Okay, so I want to finish this lecture just by doing some examples and some like factoring review. In this section specifically, 3.2, we're still relying on factoring to like find the zeros of a polynomial, but in the next section, we'll be learning some techniques that'll help us avoid that, because I know a lot of us still don't really like factoring. So yeah, we'll be learning how to not do factoring, essentially. Okay, so let's find all the real zeros and sketch the graph of f of x equals x cubed minus 6x squared plus 9x. Also, I just realized I think I've been spelling zeros with an E here for like my entire life, and that's actually like wrong. So I hope that no famous mathematician ever sees this and it's just like, wow, you dum-dum. Okay, anyways, so first thing to notice about this f of x is that each term contains an x, right? So that should lead me to think that I want to factor out an x. So each term has an x. So let's first factor out that x then. So if I do that, I pull it out to the front, and I have, taking an x out of this leaves me with x squared. Pulling an x out of this term gives me a minus 6x, right? I took one out. And then from this term, that just leaves me with plus 9 here. Okay, so now that I've factored out this x, that leaves me with a quadratic. So next thing to notice is I have a quadratic. And we do know what to do with quadratics now, right? You can either solve this by factoring or by using the quadratic formula. I will go with factoring here because hopefully we all know how to plug into the quadratic formula. So factoring the quadratic, there's all the methods you know, either setting up your bubbles, like I tend to do, or you can do the cross method, that way works as well. So I need factors of 9. That sum to -6, right? Well, conveniently, I could just do -3 times -3, right? -3 times -3 will give me positive 9, and it will sum to -6. So if I do the -3, I just write it like this. minus 3 here, minus 3 here. And so then these are actually the same term, right? So I do want to combine those into just one term, and I'm going to have x times x minus 3 squared, right? Because I have two of them. And so that's the factored version of my polynomial. So then from there, I can find the real zeros and I can sketch the graph. So let's do that on the next page. I'll copy my function in the factored form. Right? Double checking. Yes. Okay. So finding the zeros, I have to set each of my factors here equal to 0. Like we've done before. So this first one is very easy. It's just x equals 0. There's nothing to even solve there. And the second one is this x minus 3 squared equals 0. And so there's a couple of ways you could do this. You can square root both sides. So take this square root like this of both sides. Square root undoes my squared here. So I have x minus 3. Square root of 0, that's just 0. Normally I would do the plus or minus, but because it's 0, we don't need to worry about it. So then all I need to do is add that 3 to the other side. And that'll give me x equals 3. But remember, because I had this squared here, this one has multiplicity 2. And this one just has multiplicity 1. Okay, so if I'm just listing the zeros, my zeros are zeros with no e, x equals 0, and x equals 3. Okay, now let's sketch what the graph looks like. So one of the first things that I always like to do is just plot these zeros because I know that I have those points. So I have an x-intercept at x equals 0, and I also had one at x equals 3. Okay, and then maybe it's easier to look back at our original equation. Applying the leading coefficient test, I have an odd degree, and again, this is just 1. So odd degree, positive sign. So I'll write that down, odd degree. Positive sign. So that means that because it's odd, it starts down here. Because it's odd and positive, starts at the bottom, goes up, has to pass through these. I didn't do a very good job of that, but starts at the bottom, passes through this one, turns around, hits this one, but it's a bounce, remember? So comes back up like that. It's a little bit shifted here, but that's essentially what it looks like. Okay, so let's look at another example. F of x equals 2x to the 4th minus 2x squared minus 40. And we want to find all the real zeros and sketch the graph once again. So remember from our factoring lecture, this looks like a quadratic in disguise, right? I have this no x term, I have this x squared term, and I have this x to the 4th term. where the highest one is twice as much as, twice the degree of this middle term here. And I only have 3 terms, so it resembles a quadratic. So remember, like quadratic in disguise. So let's first factor out a 2, because you can see that there's a 2 in all of my terms, so that'll simplify things. So let's first factor out a 2. And that will give me 2 times x to the 4th minus x squared minus, pulling out a 2 from 40, that's going to leave me with 20. Okay, so then when we see a quadratic in disguise, we want to make a substitution. Substitution. And remember, what we usually did was let u equal whatever this is in the middle here. So in this case, we'll have x squared. Then u squared, by squaring both sides of this equation, u squared is going to be x to the 4th, right? So then we want to plug in our new variable, plug in u. So we're left with 2 times x to the 4th, that's now u squared. X squared, that's now just u. So minus u, minus 20, that's going to stay the same. Okay, so once again, we've reduced to a quadratic. We want to factor this quadratic. So 2, set up my bubbles. I want factors of 20, factors of negative 20 rather, factors of negative 20 that sum to negative 1 in this case, right? There's no coefficient on my middle term here. Sum to negative 1. So if I think about my factors of 20, where I have one positive and one negative one, so that they multiply to negative 20, I could do negative 5 and 4. I could do negative 4 and 5. There's other ones I could do negative 2 and 10. I could do negative 10 and 2. But we've already listed the ones that are going to sum to negative 1. So you pick this one, because if I have negative 5 and have positive 4, that'll give me a sum of negative 1 and multiplies to negative 20. So just filling that in, I have u minus 5, u plus 4. And then at this point, we'll plug back in for x. Because our equation is f of x, so we want to leave it in terms of x. So the factored form of my original equation is plugging back in for u was x squared. And then again, plugging back in for u is x squared plus 4. Okay, so now that we have it factored, we want to list the real zeros. So let me copy my equation one more time. 2x squared minus 5 and x squared plus 4, I believe. Right, okay. So again, to find the real zeros, I set each of my factored terms equal to 0. And the 2 here I don't need to because it's not gonna, it doesn't have an x in it, so there's no value of x that will set this 2 equal to 0. So I just need to choose this x squared minus 5 and my x squared plus 4, set those equal to 0. So let me separate those. X squared minus 5 equal to 0. X squared plus 4 equal to 0. Let's add my 5 to both sides. Remember to always do the opposite operation. I have a minus 5 here, I have to add it to the other side. X squared equals 5. Then taking the square root of both sides, that gives me x on this side, and I want to take plus or minus on the right hand side. 5 doesn't have a square root, so we can just leave it as the square root of 5. So I have 2 different solutions here, right? I'll actually list them. X equals square root of 5, and x equals negative square root of 5. And notice that these both just have multiplicity of 1. Because this, even though it has this x squared, it gives me 2 separate solutions. You only have a different multiplicity if you have something out here. If this were squared, then you would have a different multiplicity, but we don't have that in this case. Okay, so let's solve this other equation equal to 0. I want to take away my 4 from both sides. And I have x squared equals negative 4. I now want to square root both sides. And, well, we now find that we're in trouble, right? We're trying to square root a negative number. So remember that we can't do that. Square rooting a negative number gives us imaginary numbers, which we don't deal with in this class. And I don't think you do in business calculus either. So this doesn't give me any real zeros. This gives me only imaginary zeros. So no real zeros from this side. So then on my list of zeros, I only have these ones. We disregard the imaginary ones. Okay, so then if I'm going to sketch the graph, I can plot my x-intercepts. I tend to like to do that first. Square root of 5. So square root of 4 we know is 2, so it's a little bit more than 2. But it's not quite 3, because square root of 9 is 3, so it's just a little bit more than 2. Square root of 5 would be right here, the positive one, and then we also have the negative square root of 5. And it's okay if you can't like figure out what that is. You can just throw it in your calculator, and it'll be like 2 point whatever, negative 2 point whatever. So those are my 2 real x-intercepts. Let's go back to my original equation, my polynomial. So here I have even degree, and again, positive leading coefficient. So even degree, positive sign for my leading coefficient test. So remember, that means that I have my tails pointing in the same direction, and they both point upwards here because of the positive sign. And both of my intercepts have multiplicity 1, so I just have to pass through those. Right, so my graph is going to look something like, and since it's not quadratic, it probably does some wiggle, and then comes back up like this. You get more wiggles with the higher degrees. That's what the imaginary ones do. It just gives you some bump there. Alrighty, and that'll be all that I covered today. I could do like a ton of factoring examples because they're all kind of different, but yeah. If you have questions, just shoot me an email or post them in the Canvas discussion page. Otherwise, just see you next time. Thanks, guys.